Are you ready to take your high pressure aeroponics system into the future, but you don't know how many nozzles you can run at the same time? You don't know how long you can run your tubing before it fails, or you don't know what pressure you should run at. Well, I have a special tool for you. Make sure you stay to the end of this video because I have something to share with you that you do not want to miss. Also, I'm going to reveal my future plans for this tool. You're going to love it. There are various high pressure aeroponics designs that you can use for various systems. One is, how about a vertical stack system, which is my favorite. Or you can retrofit a tower garden to use high pressure aeroponics. How about a wall garden using high pressure aeroponics? That's cool. For larger plants, you would need a bucket system to use high pressure aeroponics. Maybe your fancy is to grow microgreens with high pressure aeroponics, or maybe you need to do some cloning with high pressure aeroponics. All these systems are great for high pressure aeroponics. However, each one requires a different design and setup. You can go about the design through trial and error, trying out this, trying out that until it works. Or you can do it the smarter way by using calculations and formulas to figure out the right design. Before now, that's what I did. That method is now obsolete. You can now use the Online Aeroponics Calculator to design any high-pressure aeroponics system. It can be the vertical stack system. It can be a wall garden. It can be a tower garden. Or it can be for a large bucket system. This new calculator will save you days, will save you months, or loss of your crops just trying to figure out what will work. You will know before you invest your money and time that the system will work the first time. Here it is, the first ever aeroponics calculator released to the world. This would be a quick review of what the calculator can do for you and how to use it. In future videos, we will explain in more detail of how to use the calculator. Please feel free to comment below with any suggestions that you might have or features you want added to the calculator. After you log in, you will have access to the aeroponics calculator. From there, you can go to the missing system configurations, to the delivery system configurations, and the charging system. Warning, at this time, the application does not store your data. When you close the application, your data is lost. So be sure to enter all your values, get your results, and then when you're happy with your results, then you can close the application. Okay, first let's go through the login process. If this is your first time logging in to the aeroponics calculator, you would need to click on right below here where it says sign in, click on register here to use the aeroponics calculator, and this will create a new account so that you can use the aeroponics calculator. So this would take you to a new screen, and in this new screen you can enter your email address. So be sure to enter your email address here. So after you enter your email address, make sure that you click on Aeroponics Calculator Access. And so this screen is telling you to check your email. Make sure to check the email that was sent, because in that email, it will have the password to access the aeroponics calculator. Please give this system some time to process your registration. It might take 5 to 15 minutes before you will see an email. If you don't see an email within that time, be sure to refresh your email folder or check your promotional or spam folder to make sure that the email didn't go there. Okay, so once you get there, this is what you will see when you open that email. So it will have the username for the login, which is the same name that you use as your email address, and as well as the password to use to access the Aeroponics calculator. So when you're done there, you can click on this link to access the calculator, which would basically take you back to where you started. Please note what happens to the menu bar here when we enter the right registration password. Then click on sign in. And then right away you can see now you have access to all of the systems. If this is your first time using the Aeroponics calculator, I recommend that you first start with the misting system. After you complete the misting system, then move over to the delivery system. After you complete the delivery system, then move over to the charging system. Currently, the report is not available. Okay, so let's start with the misting system. Please notice that I preloaded the calculator with some standard values to assist you in filling out the fields. If you don't know what to use in that field, just leave the defaults for now. You can always change these defaults in the future, and the calculator will automatically update all the values because this calculator is dynamic. The first value that we want to enter into this field is the nozzle flow rate. Now remember, nozzles have different flow rate at different pressures. For us, we want to use a standard pressure of around 100 psi. So look at the manufacturer specifications and find out what the nozzle flow rate is at around 100 psi. Here that you can see that I use a standard flow rate of 0.025 gallons per a minute, and this would be at 100 psi. The next field to address is the working pressure range. Here, your working pressure range is what pressure that your system will run at. What's the minimum pressure it would be operating at, and what's the maximum pressure it would be operating. This value is mostly governed by your pressure switch. Look at the specification of your pressure switch. For most of us, that pressure switch would be set at 80 as the low pressure and 100 as the high pressure. So what will happen is that when the system drops below 80 psi, your pump will turn on. Once the pressure reaches 100 psi, the pump will turn off. So that is governed by your pressure switch. Now the next field to fill out is the nozzle count. Now don't get confused with the total number of nozzles that your system might have. The nozzle count here is the number of nozzles running on a single run. So it's possible that your system might have a total of 100 nozzles. Let's say this, that you have 100 nozzles, but you have 10 separate runs, meaning that you have every group of 10 nozzles controlled by a single solenoid. So that means that you will have 10 solenoids, and each solenoid controls 10 nozzles. That means that you will use the number 10 here, even though you have a total of 100 nozzles. So for us, we're keeping this simple. We have one system, we have one grow chamber, okay, and within that one grow chamber, we have 8 nozzles controlled by a single solenoid. So that means for our nozzle count, we will use 8. Now our next field is the misting interval. Now, let's put our nozzle count back up to 8. Let's go into the next field. Okay, so this is the misting interval. Now this is a much debatable section because someone will ask you, oh, what misting interval should you use? To tell you the truth, there isn't really one right answer for all. It varies. Even the same grow of the same type of crop requires a different spray interval. Let me explain. During the germination process, you're trying to get your seeds to germinate. Normally the spray interval needs to be extended. meaning that you want a longer spray interval to induce the seeds to germinate. As the seed develops some roots, then the spray interval during the spray time can be reduced. Okay, so even with a single crop, your spray interval can vary from the beginning to the end, where you don't keep it consistent. So for now, let's just say that we're going to have a spray on time. You know, this is when the misting occurs, is for 5 seconds. And then let's say that the time between the spray intervals are 3 minutes. So we will spray for 5 seconds and then stop for 3 minutes and then spray again for 5 seconds, then stop for 3 minutes, going back and forth. Okay, so that's what we have right now for our misting interval. But for your system, it could vary. Maybe what you're trying to grow requires very little misting. So maybe you might have only 1 second of misting. Or maybe whatever you're trying to grow is that needs a longer misting interval, then you might mist for 10 seconds. Okay, but for now, this is a good starting point of 5 seconds of spraying and then 3 minutes of no spraying. So basically, this completes all the input values for the misting system. So based upon these values, we have some results. And with those results, it would tell you a story about if your system is adequate or not. Okay, so now let's look at the results, which is on the right side. So our flow results, we see that our cumulative gallons per an hour is 0.324 gallons per minute. What does that mean? That means that in 1 hour, how much nutrient are we using? We're using basically just under 1/3 of a gallon per an hour. Now, we also have our cumulative gallons per a day. So in this scenario, with these input values, we are using 7.78 gallons per day, or basically we're using roughly 7 3/4 of a gallons per day of nutrient. And then our delivery flow is 0.2 gallons per a minute. Okay, so what does this mean? Well, this means that if we wanted to store nutrient for 24 hours, we would need at least to have close to 8 gallons of nutrient per day if we wanted to just use the nutrient once. That means that we need to have at least an 8-gallon reservoir. Okay, but if you are recirculating the nutrient, then this number is not as important. Okay. Second is the delivery flow. Now, delivery flow here is 0.2 gallons per minute. So this means that at the time when your solenoid is energized, you have 0.2 gallons per minute flowing through that solenoid, through all of the tubing to reach those nozzles. In this case, 8 nozzles. So the flow rate to deliver nutrient to those 8 nozzles in this system will be at 0.2 gallons per minute. So that completes the misting system. Now let's go over to the delivery system. So this is the delivery system. So in the delivery system, the first thing we need to enter is the inside diameter and the length of the tubing that we are using to feed our nozzles. Now, when it comes to choosing your tubing, you don't want to choose tubing that has a very thick wall. And the reason why is that your inside diameter will be smaller. So we want an inside diameter that's not too much smaller than the outside diameter of the tubing. So for most of us, we are using the 1/4 inch tubing, and the inside diameter of a standard 1/4 inch tubing is 0.142 inches. Okay, so that would be taken off of the specifications from the tubing that you purchase. So normally they would give you the inside diameter of the tubing so that you can enter into here for this calculator. After you input the inside diameter, then we need to know the total length of the tubing to the furthest nozzle. So that means, okay, now this picture is only for illustrative purposes. Now in here you can see that our worst case scenario is the tubing on the very top rack. Okay, so we have 3 nozzles here. So which length will you use? We want to use the length to the furthest nozzle. So that means that we take the solenoid, we start from the pressure tank. Okay, we start from the pressure tank from here, measure the length of the tubing along this path, going up here, and then on this 90, all along here to this nozzle here. So now we want to input the length, and so the distance from the tank to the furthest nozzle is 10 feet. Okay, so we need to input that into inches. Then 10 feet will equal 120 inches. Okay, so that's the length of the tubing in inches. Now we want to input the maximum height that the tubing is above our pressure tank. So we need to measure the distance from the top of this tank to the top of this 90. So what's the distance of this tubing? Basically, what's the difference in height? So for us, it'd be 4 feet. So 4 feet into inches is 48 inches, and that's what we will put there. So this will all depend on how you have your system configured. Do you have it on a vertical stack system, or do you have it on a horizontal plane where this might be 0? But let's say that if this is your pressure tank, it's actually mounted on the wall at a higher point, okay, and you want to know what the height should be. Well, if the pressure tank is above your system, say it's up here, then you would be using a negative number, okay? So instead of using a positive number, you use a negative number to represent the height. So instead you use a negative number to represent that the tank is above your system. Next, we need to input the fittings and the components. So what we're asking here, what we're asking is what's the maximum number of fittings and components that your nutrient needs to go through before it reaches its destination. In this case, the destination is your nozzles. Okay, so in this particular diagram, remember this diagram is also for illustration purpose. Don't follow this in building your system. This is only for illustrative purposes. Okay, so here we have one solenoid that the nutrient goes through. So down here, you put down one value for the solenoid, which is already filled in as 1, because that's a default. Sometimes you might have also a filter in the system. Okay, so I went ahead and added 1 here, even though we don't see it in the system. And then we have 2 T's. We have a T here and a T here. Okay, so we have 2 T's, and then we have also 190 here. So let's add our 2 T's. So in here we have a T, so let's add another T, and then over here we have 190, which is already 1. So that completes the fittings and the components, and these are all the input values that we need for the delivery system. Now let's look at the results based upon this configuration. Okay, so now let's go through the results of the delivery system. Now here we have the total loss. So what is the impact of this configuration and setup to our system? This is saying that this nozzle right here, okay, the pressure drop from the tank to this nozzle is roughly 13 psi. Okay, so that's the total pressure drop. So that's the worst case scenario for this nozzle. So what this means is that this nozzle here, okay, has a pressure delivery at 86.6 when we are at 100 psi. So this system will function adequately, knowing that we will have at least 86.6 psi pressure at this nozzle. Now let's say you want to refine the system, that maybe you want this here to be higher, you want more pressure at that nozzle. So what can we do? Well, that's the purpose of here. So here is saying that the loss due to height is 1.7 psi. So I wouldn't try to modify that too much to get more psi at your nozzle. Here is saying that the loss due through all your fittings is 3.4 psi. Okay, we're losing that much pressure because of the number of fittings that we have. That's not really a big count either. And same thing here, component loss, we're losing 4.9 psi. And then tubing loss. Now this is the loss, the pressure drop in the tubing. So we're losing roughly a 3.25 psi due to the tubing. And this is basically the length of the tubing and the diameter of the tubing. So notice what would happen is if we cut this length of tubing in half. So say we have now 60 inches. So I change this to 60 inches. You notice now that we have decreased the tubing loss to 1.6. So we basically cut it in half, right? That's because we actually cut the length in half. That means that we cut the pressure loss also in half. So now our nozzle is running more at 88 psi. So from here to here, we can say that we would have to reduce the tubing length, okay, in half if we want this pressure to rise to 88. So that gives you kind of an idea. Now let's go ahead and change this back to 120 inches. Okay, so now let's talk about the residence time. Now, what is the residence time? The residence time is basically the time it takes for the nutrient to leave the tank and to reach its destination at the furthest nozzle. Okay, so it will take roughly almost 10 seconds for the nutrient to leave the tank and to reach the nozzle. Okay, so we talked about this before, so I'm not going to go into great detail, but this is important when the nutrient temperature is an issue. If your nutrient is being cooled and you're trying to use that nutrient to cool down the root chamber, that means that you need to keep the nutrient running, okay, at least for 10 seconds before any of the cool nutrient from the tank will reach the furthest nozzle. Okay, so that's the residence time. And then the delivery flow is just a carryover from the missing system, which is 0.02. And so over here on the delivery is also 0.2. Okay, so that's just a carryover. And the reason why is that that flow rate is used in the calculations in the delivery system. Okay, so that completes the delivery system. Now let's move over into the charging system. Now in the charging system, it consists mainly of two things: your pump and your pressure tank or your accumulator. Okay, so these values here you can get off of the pump specifications. Okay, so make sure that you choose the specification that relates to the max amount of pressure that your pump will deliver. So in this scenario, our discharge pressure, which is the pressure that the pump will reach, would be at 100 psi. And then you have to know for that pump, what's the flow that it will deliver at 100 psi. For this pump is 0.6 gallons per minute. So it can move 0.6 gallons per minute at 100 psi. So make sure you get that right from your pump specification. And then for this pump, it uses 24 volts. And at 24 volts with 100 psi, it requires 2 amps. So you would notice that the higher the pressure, the more amps the pump will pull. So let's say this is just for illustrative purposes. Let's say that we want to run at 150 psi. So maybe that might increase our pump amp average by 50%. So this would be 3 amps if we change this value to 150. Okay, so make sure that when you input the running amperage, that you're correlating that amperage to the pressure that the pump is running at. Now let's go down to the electrical costs, and just added this because it's nice to know how much electricity is your pump using and how much is it going to cost you to run your pump on your high pressure aeroponics system. Okay, and this will help you to budget your expenses. Okay, so in California where I live, it is roughly about 16.7 cents per a kilowatt hour. Okay, so whatever is in your area, it can be 13 cents, it can be 18 cents, but roughly it's probably around 16.7 cents like it is in California. So the next thing we need to input is the pressure switch. Okay, so for us, as you mentioned already, because this value is actually from another page, another part, you know, of our system, is that we're using a pressure switch that will cut on at 80 psi and will cut off at 100 psi. So once again, this is something that comes off of your specifications for your pressure switch, but it could be adjustable based upon what type of pressure switch you're using. So the one I use, it is adjustable, and I adjust it to 80 and 100. Now we have the tank specifications. Okay, so here we need to input the total capacity of the tank. The tank I'm using, the total capacity is actually 1.5 gallons. So we'll change this to 1.5 gallons. 1.5 gallons, okay. And then here we need to input what is the maximum working pressure that your tank can operate at. So for here, we will just put 100 ps. Whoops, we will put 100 psi. Put 100 psi. Okay, and then this is the drawdown capacity. Now the drawdown capacity can be calculated based upon the values that were already entered. So right now, this value is not used, but will be used in the future if you wanted to override the calculated drawdown capacity. So right now, don't worry about the drawdown capacity. And what is the drawdown capacity? Well, the drawdown capacity is the amount of gallons, okay, that the tank will deliver between the cut on and cut off values of your pressure switch. So at 100 psi, okay, how many gallons will need to exit the tank before it drops to 80? Okay, so the amount of gallons that will deplete from the tank between 100 and 80 psi is what the drawdown capacity is. Now, it doesn't seem like it, but this section actually requires definitely a dedicated video explaining the charging system, because this system is one of the most complicated systems when it comes to the number of calculations that are performed to generate the results. Now I have a warning to give you concerning the charging system. Now the charging system, as we mentioned, all the numbers came off of the manufacturer's specifications. That means that when we look at the results, okay, of this page concerning the charging system, these results are based on calculated values, not on the actual values. So how much trust can we put in these numbers? And what I have come to discover after using this and knowing what a true system performs at, these numbers are not realistic. And why is that the case? What's going on here? Why, even though we're using the manufacturer's specification, that we're not able to accurately calculate the flow capacity, the runtime duty cycle, the pump power usage, the pump power usage per a day, the pump power cost per day, the pump power cost for 30 days, which is a month. Also the drawdown recharge time, because these are all based upon calculated values. There are three reasons why we cannot depend upon the calculated values to determine the amount of power that our pump will use or how the performance will work in our system. Number one, the specifications are inaccurate. That can be various reasons why the specifications are inaccurate. It's possible that the pump testing conditions are not exactly a replication of what we have in our high pressure aeroponics system. So that means that the specifications are only laboratory true, not in the real world true. The second reason is that it's possible that the manufacturer's pumps are not consistent from one lot to another lot. Maybe the wiring was changed a little bit, or maybe the pump itself has more weight or less weight. Maybe they're using different diaphragms. Maybe the manufacturer's diaphragms has a little bit different consistency when they performed the test many years ago. And so that means that based upon the date of the manufacturing of that pump, the performance or the specifications also change somewhat. So that's another reason why the manufacturer specification numbers don't actually fit the actual condition. And the third reason is that the pump efficiency varies. What do I mean? What I mean is that we are assuming the pump to be 100% efficient compared to when they perform the test. So it's like if you have a gas heater. 3 gas heaters can use the same amount of gas, but the heat performance, the BTUs from that unit is all different. And the reason why, because one unit is more efficient than another unit, even though they use the same gas. Same thing here. We might use the same wattage or the same power or the same amount of amps, but one pump is able to deliver more pressure and a higher flow than another pump at the same power, even though they are manufactured by the same company, but based upon different scenarios, their pumps are not consistent when it comes to efficiency. One pump might be 90% efficient, another pump might be 85% efficient. Manufacturers give themselves a tolerance, okay, and we don't know what that tolerance is because they don't tell us. Are their pumps 10% accurate from each other? Is there a 20% tolerance between each pump, or 30%? We don't know. I'm coming to learn that with the Aquatech pumps, the efficiency is not consistent. One pump might be 10% better than another pump, okay? And that's because of the efficiency of the pumps have changed, okay? So the numbers that are published are not actual numbers. They are just laboratory numbers. So because of these three reasons, we cannot actually depend upon the calculated values in the charging system, okay, screen to reflect the actual conditions. So what can we do here? We need to add a correction factor to the charging system. The correction factor will adjust the values on this screen to better reflect actual conditions. So look for this update in a future release of the Aeroponics Calculator. This problem with the actual and the calculated values not correlating with one another has led me to another solution to this problem. Why not add actual measured results to our Aeroponics Calculator? That means that our calculator will not represent what's calculated, but it will represent the real environment. Then you can compare the calculated values with the actual values and come up with the correlation factor that you can use for all of your future designs. So based upon the brand of pump you're using or the manufacturer pump, everyone's going to be different, okay? If you're able to compare your calculated values with your actual values that you are actually measuring, and the aeroponics calculator can take those values in, then now you can come up with your own correlation factor for that pump. So what I'm saying here is that the aeroponics calculator can be used to monitor your system in real time. You would know exactly what the cost would be in operating your high pressure aeroponics system when it comes to electricity, when it comes to water usage, when it comes to nutrient usage, as well as the amount of seed that you're using. So all of your inputs as well as the outputs will be monitored. So you would know exactly what that head of lettuce costs you. There would be no guesswork. When it comes to selling your product for a profit, you would know that head of lettuce costs you 50 cents to grow. So you know exactly what your profit margin is. As I said before, there will be a future video to explain the charging system. Now you're wondering, how can I access this calculator now? Go down to the description below this video and click on Show More. In the Show More, you will see the link to this aeroponics calculator. So what does this mean? This means that I will add a new section to the aeroponics calculator. In this section, it will include the cost of seeds, the cost of the nutrient that you might have, the cost of any consumables that you're using in your system. And that way, along with the electricity costs that the calculator will figure out for you, you will know the total cost or the total expense when it comes to producing any crop that you are growing. And this would be beneficial for you to track your profits and to let you know where you should focus in your business. And I hope this would be something that you will enjoy. Once again, if there are any features or any suggestions that you might have for the aeroponics calculator, please comment below and I will try to respond to everyone. There is plenty more to come on how to use this aeroponics calculator and how to take your garden into the future.